Okay, let's jump in. Imagine NASA just gave you these special sunglasses, right? Cosmic ones. And they let you see the sun's breath, basically, but in like vibrant rainbow colors.
That's a great way to put it. And that's pretty much what the PNCH mission's first images feel like.
Yeah, it's this amazing new look at something really fundamental. How the sun's outer atmosphere, the corona, actually turns into the solar wind.
Exactly. And it's fascinating because, it's not just pretty pictures. That rainbow of colors you mentioned, that's the key. That unlocks information about how the sun sheds material into space. We can't see that normally.
Right, the solar wind's origin story.
Mm-hmm.
And the solar wind, this constant stream of particles, it's so important for understanding space weather.
Huge implications.
Yeah.
Things that can affect us right here on Earth.
Definitely. So for you listening, think of this as your quick guide, your shortcut to understanding this really significant solar process. We're aiming to cut through the jargon.
And we're using the actual initial data, those amazing images straight from NASA's PNCH mission, as our source material.
So our mission for this deep dive, then, is to unpack these first results and really get a handle on the innovative way PUNCH is looking at this old mystery.
Yeah, it's a totally new approach to visualizing something incredibly complex, a new lens, quite literally.
Okay, so these dazzling first images. Let's talk about that rainbow-colored one first. It really is stunning. What are the colors showing us?
Well, that color palette, it isn't just for show. It directly maps the polarization of sunlight.
Polarization. Okay, break that down a bit.
Think of light waves. Usually they vibrate in all directions, sort of randomly. That's unpolarized. But when sunlight bounces off tiny particles in space, like electrons way out in the corona, the vibrations tend to line up more. They get polarized.
Ah, okay. Like filtering it somehow?
Kind of.
Yeah.
And the direction they line up in tells us about those particles, where they are, how they're moving. PMTH measures this polarization, and by assigning different colors to different polarization states, scientists can basically see the invisible flow. Yeah, it turns this unseen current from the sun into something like a visible river flowing out.
That's incredible. And we've got specific images here, like the WFI1 first light image from April 16th, 2025. It's got this huge view, and there's this band of light stretching across zodiacal light.
That's it, exactly. Zodiacal light. It's sunlight scattering off dust in our inner solar system. You sometimes see it as a faint glow after sunset or before dawn.
Right, I've heard of that.
And PNCH Wide Field Imager WFI1 picks it up beautifully. You can see it stretching up and to the right in that image. And the fact that we can also see distant things, like the Hyades star cluster, that V shape near the top, and the Pleiades cluster down to the lower right, it tells us the instrument is really sensitive, which is exactly what you need to see the faint structure of the early solar wind.
Okay, and then there's another one, WFI3, also from April 16th, another wide view, but the zodiacal light looks different, going up and to the left this time.
Correct. Because WFI3 is another imager, looking from a slightly different spot, gives us a different perspective. In that image, you see the Pleiades again, but over on the left. And way over on the far right, there's this tiny, faint smudge.
Yeah.
That's the Andromeda galaxy.
No way, Rick.
Yep, our closest big galactic neighbor.
Yeah.
And up top, you can spot Cassiopeia, the sort of stretched out W shape.
It's an amazing detail.
It is. And seeing the zodiacal light from these slightly different angles already hints at how Popion and TH will combine views to build up that 3D picture later on. It's seeing the wider solar system context, too.
Okay, so that's what PNCH is seeing. Let's dig into how, the mission's name. PUNOH, polarimeter to unify the corona and heliosphere. That word unify feels important.
It really is. The whole point is to bridge the gap in our understanding between the sun's corona, its super hot outer atmosphere, and the heliosphere, which is the huge bubble the solar wind creates in space.
Bridging that gap.
How? By doing something that's never been done before. Mapping that entire transition from near the sun way out into the solar wind in 3 dimensions.
3 dimensions? That sounds like a huge leap. We usually just see flat pictures, right?
Exactly. Think about pictures of solar eruptions, CMEs. They look like flat clouds expanding.
Yeah.
But are they really flat clouds? Or are they more like, say, expanding bubbles? Or maybe complex twisted ribbons? We don't really know for sure from 2D.
Ah, I see. So the 3D view tells you the actual shape and structure as it travels.
Precisely. And that's absolutely critical for understanding how these solar storms evolve and, crucially, for predicting their potential impact if they're heading towards Earth. It changes the whole game for space weather models.
Going from a flat photo to a full 3D movie of the event.
You got it. A dynamic understanding.
And the key technique is that polarized light again. How does measuring that from different places give you 3D?
Well, it's a bit like how our own two eyes give us depth perception, right?
Okay.
Seeing something from two slightly different angles lets our brain build a 3D image. QNCH does something similar, but with 4 spacecraft eyes.
4.
Yeah, 4 small satellites. Each one measures that polarized sunlight, scattering off particles, but from its own unique viewpoint. The subtle differences in how the light is polarized from each viewpoint contain information about where those scattering particles are in 3D space, their density, even their speed. Things we couldn't disentangle before.
So combining the data from all 4.
Let scientists reconstruct the 3D structure, trace the solar wind as it's forming and flowing outwards.
Got it. So not just one big satellite, but a team, a constellation of 4 small ones.
Exactly. A coordinated constellation.
Right.
And they carry 2 main types of instruments.
Right. You mentioned the wide field imagers, the WFIs. There are 3 of those.
3 WFIs, yes. They're the heliospheric imagers, looking at the bigger picture, the fainter outer corona, and the solar wind stretching far out, capturing that wide context.
Any other type?
The other is the narrow field imager, the NFI. There is one of those.
Narrow field. So zooming in.
Sort of. It's actually a special type of telescope called a coronagraph. Its main job is to block the incredibly bright light from the sun's actual disk.
Like putting your thumb over the sun.
A very sophisticated version of that, yes. By blocking the main glare, it can see the much, much fainter details of the inner corona, right where the solar wind starts.
Okay, so NFI for the close-up origin, WFIs for the wider outflow. Makes sense.
And putting it all together, that's the challenge of the power.
Yeah, combining data from 4 spacecraft into one coherent 3D view sounds complex.
Oh, it is. The fully processed data will involve a lot of work, merging those viewpoints, removing background signals, instrument effects.
But these first images are more like, okay, the cameras work.
Exactly. They're crucial first light images. They confirm the instruments are in focus, they're sensitive, they're basically working as designed. Now comes the detailed calibration phase. That's where they'll fine-tune everything to pull out even more subtle details from the corona and the wind.
Speaking of tests, there was that cool image from the NFI, the narrow field one, where it caught the moon, April 27th, 2025.
Ah, yes, the moon transit.
It looked weirdly bright, though, almost like a full moon, even though it was a new moon phase.
Why was that?
That's Earthshine, a really nice example of it.
Earthshine?
Yeah, even though the side of the moon facing us is mostly dark during a new moon because the sun is behind it, from our perspective, that side is still getting lit up by sunlight reflecting off the Earth.
Ah, so the Earth acts like a big lamp for the moon.
Exactly. And the NFI is so sensitive it could pick up that faint reflected Earth light illuminating the dark side of the moon.
That's neat, but it wasn't just a pretty picture, right? There was a reason for looking at the moon.
Right. The main purpose was technical. They needed to check that the moon, as it orbits, wouldn't regularly block the NFI's view of the specific part of the corona they need to study.
Making sure it doesn't get in the way of the actual science.
Precisely. And the test showed it won't be a problem. It confirmed the viewing geometry works out for continuous observation. And in that moon image, you can see structures, like a dark circle, bright wings. What are those?
Okay, so the dark circle in the middle, that's the shadow of the NFI's occulter. That's the physical disk that blocks the sun.
The thumb.
The thumb, yes. Then the bright, sharp ring right around it is caused by diffraction light waves bending around the edge of that occulter. It's an optical effect.
Yeah.
The fuzzier, larger, hazy circle outside that is probably stray light bouncing around inside the instrument a bit. And then beyond that, you get to the dimmer region, which is the actual sky background the instrument is seeing, less affected by that internal scattering.
So looking at all that tells them the instrument is behaving as expected, the occulter is working, they understand the stray light.
Exactly. It's a diagnostic image. Confirms the core function, blocking the sun, seeing the faint stuff around it is working really well. Successful test.
Okay, so stepping back, big picture. What are the main goals for PUNCH now that things are working? What impact could it have?
Well, the number one goal, as we've kind of circled around, is to finally reveal how that transition happens, how the sun's corona continuously expands to become the solar wind. Using this polarized light technique gives them a way to make, essentially, high-res, full-color maps of that whole process.
Not just static maps, right? Seeing it evolve.
Seeing it evolve, seeing its structure in 3D. And with that wide-angle view from the 4 spacecraft, tracking it as it propagates out.
And the impact.
It should give us a much, much deeper understanding of space weather, how the sun influences Earth, other planets, our technology in space. It's about seeing that connection in a whole new way, literally seeing it differently.
Okay, let's try and sum this up. It feels like the key things to take away from this deep dive are PCH is delivering these truly stunning first images. That rainbow view showing polarized light is amazing.
Mm-hmm.
Its whole approach using 4 spacecraft, mapping this corona to wind zone in 3D for the first time, that seems like the real game changer.
An absolutely fundamental shift.
And all this could basically revolutionize how we understand the sun's effect on, well, everything else in the solar system.
Right. And that leaves us, and you listening, with something to think about, doesn't it? If we can now see the solar wind's structure and flow in 3D,
Right.
visualize it in this detail, how might that change things? Not just our science models, but maybe how we plan future space missions,
Yeah.
how we predict space weather, maybe even how we protect astronauts or satellites. It really opens up a new window.